It's now time to move on to our next presentation, which will concern the polysaccharide grid for improved stiffness and will be in fact a joint presentation between Cargill and CTP. So our two presenters are Richard Thalhofer from Cargill, who is a development specialist for packaging applications at Cargill Bioindustrial, which is located in the European Center of Experience in Krefeld, Germany. Richard's background is paper technology and business administration. Jérémy Viguié has been working at CTP for 7 years, and holds a PhD in paper physics. He is working on characterization of physical properties of board, packaging papers, or tissues, and his research activities contribute to a better understanding of the relationships between the end-use properties of paper and its fiber network structure or microstructure. So, Richard, Jérémy, the floor is yours.
Thank you very much, Caroline, for the introduction. I had the pleasure to lead the work package focusing on the reduction of the packaging weight, and I will mainly introduce you to the objectives and the concept of the work package, and then hand over to Jérémy, who will present the really interesting and innovative results, the printed polysaccharide grid for improved stiffness. Some words about Cargill. Cargill is a multinational, privately held company with around 160,000 employees all around the world. For more than 150 years, Cargill is providing agricultural products and solutions to food, feed, and industrial customers. And since Cargill is aware about the dynamics in the green economy, Cargill founded a dedicated business unit called Cargill Bioindustrial to contribute to that challenge appropriately. Cargill is well known in the paper industry as a supplier of starches, starch-based solutions for wet end applications, sizing, or coatings, but our ambition is to rise above this tradition. Next slide, please. Caroline. So I just want to point out that the portfolio of Cargill is much broader. So the portfolio of raw renewable materials is much broader, and this can contribute to the green economy of the future. So, for example, proteins, oils, and fats, plasticizers, emulsifiers, solvents, or thickeners, as mentioned before. All right, then next slide, please. So you can reveal the whole slide, Caroline. Thank you. So the objective of the work package was to reduce the basis weight of the packaging material while improving the stiffness to achieve self-standing flexible packaging. And how the idea how to do this was to print a polysaccharide grid onto the paper compound, or the compound of the barrier coatings mentioned before and the paper. The logic was to additional thickness of the compound by a low weight grid of a stiff material provides a higher stiffness. In numbers, we aimed on the reduction of 10% of the basis weight while increasing the bending stiffness by around close to 60%. Okay, next slide. To achieve this, for partners, Alstrom-Munksjö, CTP, Beauregard, and Cargill split up the work package into 2 tasks: the specification of the base paper and the printed reinforcement grid. Next slide, please. The paper substrate specification. So this is actually a more traditional paper application, or the more or less common approach to improve the stiffness in the paper industry. The objective was to reduce the basis weight but with suitable mechanical properties for packaging applications. So wet end trials were carried out by Alscher-Münchsjö with cationic starches and MFC separately and in combination. Next slide, please. And the outcome was that bioadditives can improve some mechanical properties. So the internal cohesion, the elongation, and the tensile strength, but it was not possible to counterbalance the basis weight reduction with regards to tear and tear resistance and stiffness. So in a nutshell, the traditional approach was not good enough to achieve the required improvement in stiffness. So more innovation was required. And so, Jérémy, thank you. The floor is yours.
Thank you, Richard. I hope you hear me well. Okay. I'm sorry. Good morning, everybody. So for printing the start grid on the paper surface, we use the screen printing, which is a widely used industrial process. And because we want to obtain grid thickness grid with really high thickness and thickness higher than 15 microns. And so we printed a modified starch formulation from Cargill on just a paper from Alscher-Münchsjö. And we printed several grid patterns, like orthogonal patterns with different covering ratios from 20 to 75%, and some specific grid patterns like honeycomb, reentrant, or sinusoidal. And the last two patterns, we expected some specific bending performance because of their oxetic character. And Karin, you can make the next slide with a short movie. I'll let you start the movie. Okay, thank you, Carrie. So here on the left there is a picture of the cross section of the printed paper after a iodine staining. So this is the paper and the printed layer on the paper. As you can see, the printed layer was quite homogeneous with a thickness higher than 15 microns. And on the picture on the right, you can see also that the printing resolution was quite good. Next slide, please, Caroline. Thank you. And systematically, we observe for all the type of grid and for all the covering ratio, the printed paper took an expected 3D topography as seen in the little movie, and where the printed lines form valleys, as you can see in the picture. And the mountain part corresponds to unprinted zones. And next slide, please, Caroline. And when we changed the covering ratio, as expected, the basis weight increased slightly, whereas the thickness was significantly and sharply improved. from around 60 microns for the paper itself to 250 microns for the paper with 50% of covering ratio. So it is really huge. And next slide, please. Thank you. And we measured this thickness by a specific device developed by CTP, which is a 3D map. And you can see that the 3D topography we obtained was quite regular and quite homogeneous. Next slide, please. Okay, and thanks to the this increase of the overall thickness of the paper, we can improve really sharply the mechanical performance, and particularly mechanical performance in bending. And we measure the bending resistance by performing 2-point bending tests, illustrated in the picture here. And we measure the bending moment as a function of the curvature, and we plot all the data on the two graphs. We measure the bending moment in the machine direction and in the cross direction, and the dashed line correspond to the paper itself, and the other curves correspond to the paper with the different covering ratios. And as you can see, the bending performance was multiplied by a factor 2 at 28% of covering ratio, and by a factor 3 for a covering ratio of 50%. So it is really a huge improvement of the bending performance. And in the next slide, thank you, this is a table with all the data, where you can see the huge improvement of the bending stiffness between the paper itself and with the printing and the different covering ratio. But there is no significant evolution of the tensile properties. The tensile properties remain, tensile performance remained quite constant. So the green printing improved specifically the bending performance. Next slide, please. Thank you. So then we studied the potential of other type of grid patterns, and we compare the patterns at the same covering ratio of 28%. And so we have you have here the picture of each pattern we obtain, each printed paper we obtain. You can see that in each case the printing was quite suitable. The 3D topography we obtained was quite regular and homogeneous. And in the next slide, you have a table with the main results. So you can see that the thickness was a little bit increased compared to the orthogonal pattern. And for the bending stiffness, also the bending stiffness tends to be higher, particularly with the sinusoidal pattern. But at this moment, we need to deeply investigate the relationship between the pattern and the mechanical performance, and specifically the bending performance. So we are currently working on that. And next slide, please, Caroline. Thank you. After that, we studied the relevance of our approach for other types of papers, like tracing paper or blotting paper. And you can see that in both cases, the bending stiffness was significantly improved. So it seems that this approach of grid printing is also effective for denser paper or for more porous substrates. Next slide, please. Thank you. But now we want to understand better the contribution. Okay, thank you. The contribution of the grid to the improvement of the performance, because the performance in bending was largely higher than expected when adding a grid of only 15 micron thickness, and this is because of the 3D topography and of the formation of the 3D topography. And in order to try to explain the relationship between the 3D topography and the bending performance, we can draw a parallel with the embossing of a metal plate, which is a strategy to improve the bending performance of the metal plates. It is a quite a cheap strategy, but it is a relevant strategy. Okay, can go on the next slide. Thank you. And now, in order to go deeper in the understanding, we design a specific experimental setup with XY table and a syringe to deposit the starch formulation on the paper and to deposit more starch. As you can see in the picture here, the printing quality was quite lower than with the screen printing. Caroline, but we can follow the deformation. We can follow the evolution of the structure during the drying, and I can show you a short movie. Caroline, you can just click on the, yes, you have to go back from 2 slides, please, to remove, yes, thank you. Okay, and then you can start the video. Okay, so no problem, but on the video you can see a significant drying shrinkage of the printed line and of the overall paper sheet. And because of the shrinkage of the paper sheet, the paper tends to buckle between the printed lines. Okay, thank you, Karen. So by printing a grid on the paper surface, we can significantly reduce the paper basis weight. And just by using starch, which is a few quantity of starch, because for a covering ratio of 28%, we use only 7 grams per square meters of starch. And starch is a highly available product, and which is commonly used in paper making as an additive. And domains which are potentially concerned as numerous, like flexible packaging, but also stiff packaging with folding board boxes, cups, clamshells, or why not corrugated board? Why not making the flute by printing, by using this specific behavior of the paper with the starch specific interaction starch paper. Other domain like tablecloths, envelopes, wallpaper, edition. Even if we need to consider the impact of the basis weight reduction on the optical properties, for example, and especially on opacity. Okay, thank you for your attention.
Thank you, Jérémy, and Richard for this very interesting presentation.